This is the practice test to prepare you for the real test. I apologize for the audio, but I don't have a good microphone available right now. First off, remember all the formulas will be provided. Here are some formulas, and I'll begin. So in the first few questions, we have a rubber band car powered by a string. It's wrapped around the car's rear axle. String pulls with force given below. So the first thing I want to figure out is how much torque does the force of the string impart to the wheels and axle. Here's my torque formula, force times radius. Now you might want to put this in, if you're not good at algebra, put this in a little triangle. The T would go on top, F and R would go on the bottom. You're going to need that multiple times. So the torque that the force of the string imparts is equal to the force of the string multiplied by the radius at which it applies the force. Here's the string force times the axle radius, because the string is attached to the axle. It's applying the force at this radius. And there we go. So it says it's correct. The units are Newton meters for torque. How much force do the wheels exert against the road? Well, there's this much torque in the axle. We just figured that out. And if torque equals Fr, then force equals torque divided by radius. So this force is going to be the torque in the wheels divided by the radius of the wheels, because this force is exerted against the road, so we use the wheel radius. We use the radius at which the force is being exerted. The minimum radius that the wheels can have without spinning out. So whether the wheels spin or not depends on whether they apply more force than friction can handle. Here we're given the force that friction can handle. So we can calculate the size wheels we need to have in order to have that much force. Then we'll be at right up the upper limit of how much force they can have. So again, we're looking for radius. So we use the torque formula again to solve for radius. Radius is going to be torque divided by force. The amount of torque in the axle is 0.1, and the force that we want these wheels to have is the force of friction, 1.4. Torque divided by 1.4, and that gives us 0.071, and the unit should be meters. For the previous question, it's force. The unit should be newtons. Newtons is capital N since it was named after Newton. Any wheels smaller than this are going to give us a bigger force. Any wheels bigger than this are going to give us a smaller force than the force of friction. 11 through 19. These questions, you can read this. You really should read what's in blue. I'm not going to keep the video shorter. The data shown here relate to the question there. So these distances, somebody's winding up a car by putting the wheels on the ground and rolling the car backward. They roll it ultimately 3.06 meters. And as they do that, the rubber band gets tighter and tighter. These forces get bigger and bigger until when they've rolled it back 3.06 meters, the force measured at the edge of the wheel is 3.5 newtons. So that force gets stronger and stronger and stronger. The first question, we're given this. We're given the car's mass in grams, we're given the maximum velocity when the car is released, and we're given the drive wheel radius. Car's mass in kilograms is just going to equal, type in equal, the number of grams, the mass in grams divided by 1,000. And the unit should be kilograms. The average force that's applied to the wheels during winding, well, we've got a table of forces, and we just need to average those forces. If you type A, V, E, and options will pop up, you can click on average. And it already opens the parentheses for you. If you type in the whole word, you need to open the parentheses yourself. Then you go over and you select all the numbers you want to average. I want to average all these forces from 0 all the way up to 3.5, and then I can just hit enter. I don't have to finish up close my parentheses. That'll be done for me. So there, that the average force of all those forces is 1.48, and the unit should be newtons. As a student winds a car, he or she does work. Over what distance does he or she do that work? Well, the car is being wound by pushing it backward over this distance that's shown here. Here's the distance rolled by the wheels. The student pushes 0 meters, 0.3 meters, 0.68, finally pushes a total distance of 3.06. And not only is this the force measured at the edge of the wheel, this is how hard the student has to push to get the car's wheels to turn. So this is the total distance that the student pushes, and this is at the very end how much force they apply. So the distance is equal to that, and the units should be meters. How much work does a student do? Let's go up to the top. The work formula is force times distance. You've already calculated force and distance. You've got the average force here, and you've got the distance there. So the formula is the average force times the distance. So the student pushes with an average force of 1.48 newtons. That's the average of all these, multiplied by the total distance, 3.06. And, oops, sorry, 106. And the units are going to be joules with capital J. I've been doing lowercase j, but it's named after joule, so it should be capital. How much potential energy is stored in the car? The potential energy stored in the car is equal to the work that the student has done on it. So the student does all this work, putting in 4.5288 joules of doing 4.5288 joules of work. So the potential energy is just going to be the same thing. The student is storing energy in that car by doing work. The car's maximum kinetic energy. We need the kinetic energy formula. It's right here, 1/2 mv squared. And if we want to do maximum kinetic energy, we need to do that when this is the biggest. Well, the mass is never going to change, but the velocity is. We need the biggest velocity. So I'm going to start putting things in. Equals 1/2, which is easiest to just do a 0.5, times the mass of the car. We always use kilograms in these formulas, so don't put the 240 in. You need 0.24 times velocity squared. And let me go down a little bit. There's the car's maximum velocity. Click that. Do Shift 6 to get the caret symbol there. So I have 1/2 times the mass times the velocity squared. And that's the car's maximum kinetic energy. Energy is joules. Energy and work are always joules, capital J. Efficiency. There's a formula for efficiency up here. Efficiency is the energy output divided by the energy input. And the energy output, so which comes first? Think about this. Which comes first, output or input? Well, you can't get stuff out until you put it in. So the input comes first. We're looking at energy in both cases, so it's one of these J's here. Here we've got a big number, which is the work the student did, and it's also the energy stored in the car. That happens first. That's the input. The student is putting energy into this car, this much energy. The kinetic energy, that's what we measure later when the car starts to move. That's based on how fast it's going. That's the output. So the efficiency is the output divided by the input, the potential energy. And right now this is showing as a decimal. If I just, let's see, change this to, I don't know, we change the format number. So there, if you just put the formula in, you're going to get a number, 0.1656, which is 16.56%. If you want to convert it to a percent, you can click on that. It's fine with me, but I'll also take it as a decimal. It doesn't really need any units unless you'd like to put the percent over here, and then it needs to be 16.56. What velocity would this car have if it had twice the maximum kinetic energy. This one's kind of involved. If you know the kinetic energy of a car, you can calculate velocity. Just like we knew the velocity here and we calculated the kinetic energy. Really, you should be able to, at this point, take the kinetic energy formula and rearrange it to solve for velocity. But I've done that for you. So here's the formula we need. Velocity equals the square root of 2ke over m. Now, the question isn't just asking us to do the square root of 2ke over m, because it's asking, what about if it had twice the maximum kinetic energy? I'm going to type in square root, or I'm going to start to. As I start to type this in, I see this. That's the square root symbol, SQRT. And I want to do 2 times the kinetic energy. Except here, I don't really need these parentheses, but I'm doing them just for fun, just to keep things organized. 2 times the kinetic energy. But the kinetic energy here is twice the kinetic energy, so I'm going to put in these parentheses, 2 times. I'm going to go up and click on the kinetic energy of the car. So I've doubled the kinetic energy, multiplied by 2 times double the kinetic energy, divide that by the mass of the car, and close my parentheses. Now I've got the answer. That's how fast it would go if it had twice the kinetic energy. So once more, just done this, except instead of ke, I put in 2 times ke. So it's 2 times 2 times ke. You could do 4 times the kinetic energy of the mass. I'll do it that way just for kicks. So let me get rid of all this. I'll leave the square root. 4 times, click on the kinetic energy of the car, divided by the mass of the car. And I still get the same answer. And the units would be, for velocity, meters per second. The maximum torque, this one doesn't really fit. All these go together, and then this one, torque. So torque, when we're going to calculate torque, there's a formula for it. Torque equals force times radius. Maximum torque, we want to do it with the maximum force, maximum radius. Well, the radius doesn't really change. I need to go looking for a force here. If I scroll up here and look for forces, there's one, 1.48 newtons. But this is the average force applied to the wheels during winding. I want the maximum force. So I have to go over here. Force exerted by the edge of the wheel is 0, 0.2, 0.3. The maximum force is 3.5. That's what I want. So 3.5, that's my force, times radius. And this force, 3.5, is exerted by the edge of the wheel, so I need to multiply by the wheel radius, which is provided right there, drive wheel radius. And the units are the unit for force times the unit for radius. Radius is a distance, so it's meters. The last set of questions relate to a car that has been videoed, and somebody watched this video and they watched the car traveling across the floor at the 0 meter mark, the half meter mark, the 1 meter mark, the 1.5, and they recorded the video frame number for each of those. Frame rate of the video is 240 frames per second. The car mass is 0.17. We've got to calculate all this stuff. First thing to do is to do the total elapsed time. And to get the total elapsed time, we take first we figure out how many frames have gone by. 1,000, that's the frame number when it gets to the half meter mark, minus 275, that's the frame number when it started. That's going to give me the number of frames. I want to put dollar signs in front of the 29 and the age. Oh, and I'll tell you why in just a minute. And I want to put all this in parentheses. So since this minus this, 1,000 minus 275, that's not going to give me time. That's going to give me frames. I'm going to get 725 frames. Now, if there are 240 frames per second, each one is a 240th of a second. So what I have here is 725 frames, a 240th of a second each. So I have 725 240ths. That's how many seconds have gone by. So it boils down to getting the number of frames that have gone by, this minus this, divided by 240. And that tells me the elapsed time. That's how much time went by from when it was at this point to that point. Now I can copy that formula down, and it's going to give me correct answers all the way down. The reason it's going to do that is because, I'll just click on this one, by putting in the $sign here and here, it's now going to take the current frame number and subtract the starting frame number. That gives me the total number of frames since we began. That divided by 240 gives me the total time. When I go down here, now it's taking the current frame minus the starting one again, giving me the total frames divided by 240, which gives me the total time. So this is, if you started a stopwatch at the beginning and stopped it at the end, it would say 10.9 seconds when the car got to the 10-meter mark. It's pretty long, actually. Now, here let's make sure that's right. H30 seems a little long. Well, let me do this, make sure it looks right in a minute. So now the time interval for just the segments. So this is the total running clock, and this is the time for the first half meter, and then we'll do the time for the second half meter, and then for the third half meter. So now I've done the hard work. Now I can just do the current time minus previous time. Copy that down. This is how long it took for the car to go first half meter, second half meter, the third half meter, the fourth half meter, the fifth half meter. This is the time right here minus the time when it was a half meter back. So these are our delta T's. This is the change in time for each half meter. Now velocity. Velocity formula is at the top. Velocity is distance divided by time. And I'm going to change this to velocity for previous half meter segment. This isn't the total velocity or the average velocity. Same thing with acceleration. It's what was the velocity for the first half meter? What was the velocity for the second half meter? So it's distance divided by time. All these distances for the first half meter was half a meter. Second half meter went from 0.5 to 1, another half meter. The third half meter went from 1 to 1.5. The distances are always going to be 0.5. And the time is going to be this. This is how much time it took to go for the first half meter. Now I'll copy that one down. And I've got all the velocities. So this is 0.5, that's the distance, divided by this time, which was the time to go from 0.5 meters to 1. And this one right here, this is half a meter, which is the distance it traveled during the segment, divided by 0.833, which is this minus this. It's the time for that segment. So I've got all my velocities. Now I need my accelerations. Acceleration is change in velocity over change in time. I've already got the change in time done. I've been using that one. The change in time, the delta T, that's this column, column K. I just need to do the change in velocity. The velocity right now is this. I'm going to subtract from that the velocity before. This is giving me the change in velocity over the last half meter segment. I divide that by the change in time. I could, if I wanted to, take the current time, subtract the previous time. And that would work. That worked fine. That would give me all the right answers. Retrospectively, I should have just left out this column altogether because it confuses people. But I thought it would save you some time because we've already figured out the change in time. Instead of this minus this, I can just click on that. And I get the same answer either way. If we look at what this is doing, the velocity is going up, 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 and it gets to 6 right there. And the acceleration is going up, staying positive at least. It kind of goes up and down and up and down. Here it goes up, then it goes back up even higher, then it goes down, but then it goes negative. Let's answer the questions now. Car's maximum velocity. You just look at the chart. Here's the velocity column. We look for the biggest number in that column, not the last number, the biggest number. It goes 3.87, 5.21, 6, 5.81. There it is, 6. So I'm just going to type equal sign, go over there to that 6, hit it, hit enter, and my 6 appears there. The units are meters per second. Maximum kinetic energy, look for the kinetic energy formula. There it is, 1/2 mv squared. So 1/2, 0.5, times maximum mass. That doesn't make any sense. The mass is always the same, so I just use the mass. Times, if I want maximum kinetic energy, I need the maximum velocity, which I just put up here. But that needs to be squared, so I do Shift 6 to get the caret, and then the 2. There, I've got it. Energy is joules, capital J. The average acceleration, well, you might be able to get it different ways, but I've got a bunch of accelerations. Why don't I just average them? And I go over. Oh, wait a second. Let me read this carefully. During its acceleration period, the car speeds up, the car slows down. I only want to average the acceleration during its acceleration period. I should really say during the positive acceleration period. So I only want to be averaging positive numbers. After that, the car is not decelerating or accelerating anymore. There we go. So that's my average acceleration. It should be meters per second, or meters per second squared. You can do it either way. The average force during the acceleration period. Let's see. Is there anything about force over here? No. Force. There's a formula for it. Force is mass times acceleration. The mass of the car, 1.17, times the average acceleration. That'll give us the average force. And force should be newtons. The work done by the car as it's accelerating, work is force times distance. There's the formula, force times distance. We've got the average force right here. And now we need to multiply it by the distance over which it exerted that force. So I need to figure out how far it was going when it was exerting this average force. Let me go to my table. Now remember, we're just talking about the acceleration period, which was when the acceleration is still positive. Right here, this row, this is where the acceleration is last positive, and the distance, if you look at the distance column, is 5 meters at that point. So that's the acceleration distance. After that, it starts to slow down. So I can just click on that, or I can type 5. So that's correct. And work is joules. So again, that was the average force times the distance. When it was accelerating, the distance is 5. What's the power in watts? Power, going up to the top, power, where's power? Work divided by time. So I need to know how much work it did and how much time it took to do that. Again, this is asking about the acceleration period. So I just want the time for the acceleration period. Going back over, acceleration ends with this row. So right here, this is the distance at which acceleration stopped. This is the time at which acceleration stopped. This is the velocity at which acceleration stopped. And that was the final acceleration itself. So for power, power equals work divided by time, that time. That's the, again, down here acceleration went negative. That's the time at which acceleration stopped being positive. And that should be in watts, capital W, named after watt. The average power in horsepower. To convert this to horsepower, you can either remember the conversion or type in convert watts. You don't even have to type convert, just watts to horsepower and copy this, Control C, go back, type in the number of watts. Each of those watts is that many horsepower, so I'm going to multiply the number of watts times, Control V. There's the number I just copied, and there we go. And the units are HP, horsepower. Now I want the average acceleration once it begins to slow down. Average. Go over and look for all the negative accelerations. Hit enter, and I get negative 2.14 meters per second squared, or meters per second. Then the force of friction. Well, the reason it has this negative acceleration is because friction is slowing it down. So if I want to find the force of friction, let's see, how many formulas for force do I have? I've got F equals ma, I've got work equals Fd, but I've got torque that's got force in it. What else? That's it. So the one that's going to help me here is ma, because I have them both. I have the mass of the car, and I have its acceleration. The mass is 0.17 kilograms, and I multiply that by the acceleration that's being caused by friction. And there we go. That's the force of friction when it's slowing down. That should be newtons. If you're pretty sophisticated, you may have noticed I've cut a few corners here. I used to have the word net put in here, because when the car's accelerating, it's got a net force acting on it, which includes its friction and it includes a rubber band. And if we're talking about the power output, some of that power is being masked by the friction. So maybe the rubber band's putting out more power, but then friction is sucking some of that up. So these would all be net. And that's it.